At this point, we're going to review the cognitive phenomena that later in the course we'll aim to understand in terms of brain anatomy, physiology, and chemistry. But I'm going to begin with some general comments on the characteristics of the brain. It can learn many different types of behaviors, but if a computer can be programmed to perform a behavior, it can often do it better than a human being. There are some odd things about the brain that it will be nice to understand better. And we have to bear in mind that some objects, like a camera or a computer, may perform functions that have some resemblance to brain functions. But that doesn't necessarily mean that the way these other objects perform the functions has any relationship with how the brain does them. So let's have a look at each of these considerations in a little bit more detail. The human brain can learn to perform many different types of behaviors. However, it can make occasional errors, even in tasks that have been performed correctly in the past many times. We sometimes stumble when we're walking, or mispronounce a word in conversation. And in the case of mental arithmetic, even after years of learning, most people continue to make mistakes. But we're very good at pattern recognition. For example, we can easily recognize all these different visual objects as being the letter G, despite different fonts, various distortions, and visual noise. We can tolerate even more distortion and noise if the letter appears within a known word. Our pattern recognition capabilities can sometimes find patterns that aren't behaviorally useful, like faces in clouds or faces on the surface of Mars. And the illusion can persist even when it's clear that the object is actually something quite different. Now, in this familiar illusion, we can see a vivid white triangle, although all that's actually present are three angles and three Pac-Man-like figures in a specific orientation. If the orientation is somewhat off, we can see an illusory sawtooth shape, which is still there with even more misalignment. But with even more misalignment, it doesn't actually usually persist, although now we may see the triangle again. And the triangle can be there in the absence of the Pac-Man, just on the basis of the angles of the cuts in the side of the triangle. And again, the illusion is much weaker if the lines are thinner and the angles less obvious. We also have a strong ability to establish associations between different objects or situations. Sometimes associations can be based on visual similarity. We connect these visual objects as all being birds. But associations can also be established on the basis of being used during the same event. A tent, a sleeping bag, packaged food, a flashlight, and so on are all things to be taken on a camping trip. So these items are associated by similar events despite the absence of any visual similarities. We also create associations on the basis of intellectual rules, such as the rule that warm-blooded animals that feed their young with milk generated by their bodies are all called mammals. This classification overrules even a strong visual similarity, such as the similarity between the dolphin mammal and the tuna fish. And when you're a mathematician, one of those objects on the lower right is a triangle and the other is a quadrilateral, despite their strong visual similarity. A computer is often faster and more accurate than a human, provided the computer can do the task at all. And when a computer has stored an image, it can retrieve that image with a much higher detailed visual accuracy than a human could ever recall it. However, the human recall will generally be able to identify the most behaviorally significant aspects better than a computer. And there are some superficially strange brain phenomena. For example, we spend about a third of our lives in a state called sleep, in which the brain is vigorously active, but in a way that differs considerably from its activity when we're awake. And the proportion of time spent in sleep can be 80% or more for newborns, and still about 50% at age 4. So the sleep process is unlikely to be simple rest. Some important processing is going on. Finally, we need to be very careful with our intuitions about how the brain works. As an example, think about how visual information is actually processed in the brain. Visual input comes from our eyes, which have a lens, and a retina on which images are focused. And in some ways, there are similarities with cameras that also have lenses focusing images on some kind of screen or sensor. But suppose this is the image to be processed. And suppose the camera is moved so that it points to different spots along that red arrow. Then, as the camera moves, the image on its screen will vary rapidly. If we start from here, if you were looking at the image, you'd see rapid apparent motions of the various objects in the image because the image is constantly shifting. Now think about what happens if you move your eye across the picture on the same track. The same succession of images will arrive on some particular area of the retina, containing the same apparent motions of the objects in the scene. So the image on your retina is in constant flux. But what you actually perceive is a stable image, with all the objects stationary as your eye moves. In other words, what you're aware of seeing is an extremely processed version of the images on your retina. Seeing the world in this way rather than having it appear to move around because of your own body motions is obviously better for interacting with the world. Now let me comment briefly on another aspect of brains that must make us wary of models that are too simple. If you look at where the brain is active when you're remembering a past event, a lot of different areas are participating. In fact, all the major anatomical structures of the brain play a role in recording information about experiences and later remembering them. Furthermore, when you compare brain activity during two different tasks, like recalling a past event and imagining a future event, many of the same brain regions are active. So we're not going to find brain areas that in some sense correspond with cognitive features, which is, as I touched on earlier, exactly the same as the situation in computers. An iPad, for example, can support many different features. If you look inside the hardware, you see different components with functions like processing, memory, and so on. And any one feature uses most, if not all, of the different hardware components. So if you want to understand how higher cognitive features are supported by brain anatomy, the answer will not be this piece of anatomy or physiology just supports that feature, and so on.